The Leo cluster holds secrets that even the most advanced telescopes can't fully unravel. Stretching across hundreds of millions of light years, this cosmic gathering of galaxies behaves in ways that leave scientists scratching their heads. Some galaxies move as if pulled by invisible hands. Others emit signals that shouldn't exist according to our current understanding of physics. Today, we're going to examine 25 of the most baffling phenomena in this celestial mystery box. Anomalies so strange they've sparked debates about whether we're missing something fundamental about how the universe works. From ghostly radio emissions to galaxies that vanish without a trace, each one of these enigmas challenges what we thought we knew about the cosmos. And the deeper we look, the more questions arise. Why does dark matter seem to cluster differently here than anywhere else we've observed? What could explain the bizarre temperature fluctuations in the intracluster gas? These aren't just minor curiosities, they're potential cracks in the foundation of modern astrophysics. And by the end of this journey, you'll understand why the Leo cluster might be the most important puzzle in space today. Deep in the heart of the Leo cluster, something impossible keeps happening. Galaxies vanish, not slowly fading from view, but disappearing completely in the span of human observations. Take NGC 3841 for instance. 1 year it was there, a perfectly normal spiral galaxy. The next gone, no debris, no telltale signs of collision, just an empty stretch of space where a billion stars once shone. Astronomers call these vanishing galaxies, and they're one of the most unsettling mysteries in modern astrophysics. Theories abound, but none fully explain why this keeps happening. Some suggest these galaxies might be cloaked by vast clouds of rogue dark matter regions so dense they bend light away, rendering entire galaxies invisible to our telescopes. Others propose these disappearances could stem from observational errors, glitches in data processing that make real galaxies seem to blink out of existence. But the strangest idea, that these galaxies might be getting pulled into other dimensions, warped beyond detection by physics we don't yet understand. Then there's the case of LEDA 214500. Unlike NGC 3841, this galaxy didn't vanish all at once. Over 2 decades, telescopes watched as its outer stars seemed to unravel, dissolving into the void while its core stayed intact. It wasn't a collision or a black hole's doing. There was no energy signature, no explosion, just silence. If dark matter is responsible, it behaves unlike any model we've ever predicted. And if it's not dark matter, then we're facing something even more extraordinary, a phenomenon that rewrites the rules of galactic evolution. The unsettling truth is this: every time astronomers pin down one vanishing galaxy, another disappears elsewhere in the cluster. Whatever's happening in Leo, it's not stopping, and until we solve it, we can't be sure the same fate won't one day reach our own Milky Way. While vanishing galaxies present one cosmic puzzle, the Leo cluster holds another mystery that crackles through the void: phantom radio signals with no discernible origin. These strange emissions ripple across radio telescopes as sudden bursts of energy, appearing and disappearing without warning. Unlike pulsars or quasars, which pulse with predictable rhythms, these signals arrive in chaotic, unpredictable patterns, as if the universe itself is sending encrypted messages. The first of these signals was detected in 2017 by a team studying background radiation. At first, they assumed it was interference, an earthly glitch or passing satellite. But when the pattern repeated across multiple observatories, the truth became unavoidable. Something in the Leo cluster was broadcasting, and we still don't know what. Some of these bursts last mere milliseconds, while others linger for minutes, vanishing before astronomers can pinpoint their exact location. One leading theory points to supermassive black holes. As matter spirals into these cosmic voids, it could generate shockwaves that ripple outward as radio emissions. But here's the catch: these signals don't match any known black hole behavior. They lack the energy signatures of accretion disks or relativistic jets, leaving researchers questioning whether black holes might have hidden dynamics we've yet to uncover. Another possibility: magnetars neutron stars with unimaginably powerful magnetic fields. When these stars experience starquakes, they can unleash intense radio waves. Yet no known magnetar in the Leo cluster aligns with these signals' erratic timing or strength. If neutron stars are responsible, they're behaving unlike any we've documented before. Most baffling of all is the silence between bursts. Most cosmic phenomena leave traces: residual heat, gravitational ripples, or fading light. These signals leave nothing. One moment they're there, the next gone, as if switched off by an unseen hand. Whether it's undiscovered physics, alien technology, or something beyond our current comprehension, these phantom transmissions remind us that the Leo cluster still has secrets it's not ready to surrender. Among the many cosmic riddles the Leo cluster presents, few are as unsettling as its gravity anomalies, pockets where the very fabric of spacetime seems to rebel against the laws we thought were unshakable. Einstein's theory of general relativity has guided our understanding of gravity for over a century, predicting how massive objects warp the space around them. But in certain regions of Leo, gravity doesn't just bend. It twists, contorting spacetime in ways that defy even the most refined models. Take the case of Able 1367, a galaxy group within the cluster where gravitational lensing, the bending of light by massive objects, produces effects so extreme they border on the impossible. Light from distant galaxies arcs around it in chaotic, jagged patterns rather than smooth curves, as if spacetime itself has developed wrinkles. Normally, lensing follows predictable distortions based on observable mass, but here, the warping suggests unseen forces at play, either concentrations of dark matter behaving unlike anything we've mapped, or something even stranger. The real shock came when astronomers tried to calculate the cluster's total mass using two trusted methods: measuring the motion of galaxies and analyzing the lensing effects. The results disagreed wildly. One suggested the cluster held nearly 3 times the mass of the other, a discrepancy so large it can't be chalked up to error. If dark matter is responsible, its distribution is unlike any other known cluster, clumping in bizarre, uneven ways. But some researchers speculate the answer might lie beyond dark matter, perhaps a flaw in our grasp of gravity itself. Could Einstein's equations break down at these immense scales? Then there's the eerie influence of dark energy, the mysterious force accelerating the universe's expansion. In most of the cosmos, dark energy's push is subtle, detectable only across vast distances. Yet in Leo's gravity anomalies, its effects seem magnified, as if the cluster sits at the edge of a cosmic fault line where the rules are bending. Whether it's unseen matter, revised physics, or something far beyond our current theories, these anomalies remind us that gravity, the force we thought we knew best, might still hold secrets we've barely begun to glimpse. Just when scientists thought they'd catalogued every kind of cosmic explosion, the Leo cluster delivered a curveball, a flash so brilliant it outshone entire galaxies, then vanished without a trace. On March 8, 1987, telescopes around the world captured an intense burst of light in the heart of the cluster, blazing for mere hours before fading into oblivion. Dubbed the cosmic flash, this event defied classification. It wasn't a supernova those leave behind glowing remnants for centuries. It wasn't a gamma ray burst those typically last seconds, not hours. Whatever caused this, it existed in a category of its own. Initial theories pointed to a rare quark nova, a theoretical explosion where a neutron star's core collapses into an even denser state, a soup of free-floating quarks. The energy released in such an event could match the flash's profile, but there's a problem. Quark nova are hypothetical. No confirmed observation exists, and the models predicting them remain contentious. Even more puzzling, follow-up scans found no neutron star or black hole where the flash occurred, just empty space. It's as if the event erased itself entirely. For decades, astronomers have tried to trace the flash's origin. Some argue it might have been a failed supernova, where a massive star collapses directly into a black hole without the usual fireworks. Others suggest it could have been an immense magnetic flare from an unknown type of stellar remnant. But the most intriguing idea involves primordial black holes, hypothetical black holes forged in the early universe, small enough to evaporate in bursts of energy via Hawking radiation. If one of these evaporated in the Leo cluster, the resulting flash would fit the brief, intense profile of the 1987 event. What makes this flash so tantalizing is its sheer elusiveness. Most cosmic explosions leave forensic evidence: debris, shock waves, lingering radiation. This left nothing. It flared like a cosmic flare gun, then vanished as if it never happened. Whether it was a quark nova's debut, a dying black hole's last gasp, or something even more exotic, the Leo cluster's flash remains a gleaming question mark, a reminder that the universe still holds fireworks we've yet to understand. In the vast cosmic theater, supernovae are usually the grand finale, spectacular stellar explosions that announce their presence with bursts of light visible across the universe. But in the Leo cluster, astronomers found something that defies this rule: a supernova remnant with no recorded explosion. It's like finding the aftermath of a fireworks display without anyone ever hearing the bang. This silent supernova, catalogued as SNRJ 1047+5644, bears all the hallmarks of a massive stellar death: expanding shock waves, glowing filaments of gas, and heavy elements scattered across space. Yet, when researchers combed through decades of observation records, they found no trace of the brilliant flash that should have accompanied it. Supernovae are supposed to be impossible to miss. Some shine brighter than entire galaxies for weeks. But this one left no paper trail in the light. So what could explain a star's death without the fireworks? One chilling possibility involves primordial black holes, hypothetical relics from the universe's earliest moments, small but incredibly dense. If two of these ancient objects collided within a star, they might have devoured it from the inside out, collapsing the core so abruptly that the outer layers imploded without the usual explosive release of energy. No light show, no dramatic finale, just a star vanishing into darkness. Another theory suggests an ultra-rare, failed supernova, where a massive star's core collapses directly into a black hole, swallowing so much matter so quickly that the rebound shockwave, the engine of a typical supernova, never makes it out. It's the cosmic equivalent of a building collapsing inward without a sound. What makes this silent remnant so unsettling isn't just the mystery of its origin, but what it implies. If stars can die without a trace, how many others have slipped away unnoticed? And if primordial black holes are lurking in the Leo cluster, could they be rewriting the rules of stellar evolution right under our telescopes? One thing's certain: in a universe where even the loudest events can sometimes happen in silence, astronomers are learning to listen more carefully than ever. Nestled within the swirling depths of the Leo cluster lies a cosmic anomaly that has rewritten the textbook definition of gamma-ray bursts. Most of these energetic explosions mark the violent deaths of massive stars, one-time cataclysms that unleash more energy in seconds than our Sun will produce in its entire lifetime. But in 2016, astronomers witnessed something that shouldn't exist: a gamma-ray burst that kept coming back. Dubbed GRB 160825b, this repeating phenomenon erupts without warning, blasting out high-energy radiation in erratic bursts lasting anywhere from milliseconds to several minutes. Unlike typical gamma-ray bursts that fade forever, this one reactivates months or even years later, as if whatever's producing it refuses to stay dead. The irregularity is startling. No known stellar collapse or collision could explain such persistent, unpredictable eruptions. the energy signature tells an even stranger story. Typical gamma-ray bursts from collapsing stars show a distinct afterglow as ejected material decelerates, emitting X-rays and visible light for days. GRB 160825b leaves no such trail. Its emissions cut off abruptly, as if the energy source gets abruptly switched off. Some researchers point to magnetar neutron stars with magnetic fields a trillion times stronger than Earth's as potential culprits. When these ultra-dense objects experience magnetic upheavals called starquakes, they can release gamma-ray flares, but even the most volatile magnetars shouldn't produce bursts this powerful or sporadic. Then there's the location puzzle. Gamma-ray bursts usually trace back to young, star-forming regions where massive stars dwell. This one originates near an ancient elliptical galaxy, a stellar retirement home where explosive stellar deaths are rare. If a magnetar asterisk is asterisk responsible, it might be a relic from a long-ago collision between neutron stars, an undead remnant that periodically unleashes pent-up energy. Perhaps the most tantalizing clue lies in the burst's uneven intervals. Unlike pulsars with clockwork precision, this source erupts with chaotic timing, suggesting forces at work beyond our current models. Could it be a black hole grazing a neutron star, stripping material in violent, irregular outbursts, or evidence of exotic physics in the magnetar's crust, where quantum phenomena might trigger sporadic energy releases? Whatever's powering this cosmic repeater, it's forcing astronomers to rethink the boundaries of stellar physics. In a universe where even the most violent events usually follow rules, GRB 160825b stands as a rebellious enigma, a flare that refuses to fade quietly into the dark. Deep within the Leo cluster's swirling expanse, astronomers have stumbled upon the ultimate cosmic ghost, an object so massive it bends light like a black hole, yet refuses to show itself on any telescope. This invisible giant, detected only by its gravitational fingerprints, tugs on surrounding galaxies with the force of 20 billion suns. But when researchers point every instrument they have toward it, radio, infrared, X-ray, they find only empty space where an object of that scale should blaze like a beacon. The discovery came when scientists noticed a group of galaxies moving as if pulled by an unseen hand. Their trajectories suggested a colossal mass at the cluster's edge, yet scans revealed nothing but darkness. Normally, an object this size would be unmistakable, a supermassive black hole's glowing accretion disk, or at least the heat signature of colliding matter. But this phantom leaves no trace, not even the faintest whisper of radiation. Some theorists argue it could be a rogue black hole ejected from a galactic collision, now drifting unseen through intercluster space. Such an object would carry no stars or gas to feed on, explaining its invisibility. Others propose something far stranger, a dark star made almost entirely of exotic dark matter, a hypothetical structure bound together by forces we don't yet understand. The most radical idea, that we're seeing the first evidence of a primordial black hole from the early universe, one so ancient it's had billions of years to consume all nearby matter and go dormant. What makes this mystery so compelling is how it forces us to confront the limits of our tools. Modern astronomy relies on detecting light from radio waves to gamma rays. But here, in the heart of Leo, something massive bends the rules, challenging us to ask how much of the universe might be hiding in plain sight, invisible simply because we haven't learned how to see it. Until we solve this riddle, one thing is certain: the cosmos may be far stranger and far darker than we ever imagined. Among the glowing clouds of gas and dust that typically cradle newborn stars, the Leo cluster hosts a cosmic oddity that flips the script entirely, a nebula that shines brilliantly despite having no stars to light it up. Dubbed the phantom glow by researchers, this eerie structure defies one of astronomy's most basic expectations: that nebulae glow because of the stars embedded within them. Yet here, telescopes reveal an expansive, luminous cloud with not a single visible star at its heart. So what's keeping this cosmic lantern lit? One leading theory points to rogue photons, high-energy particles left over from ancient stellar explosions or quasars that flooded the region long ago. These trapped photons could bounce endlessly through the nebula's dense gas, re-energizing it like a celestial glow stick. Another idea involves dark matter annihilation, where hypothetical particles collide and release bursts of light. Though no known dark matter model perfectly explains the nebula's consistent radiance. Even more puzzling is the nebula's spectral signature. Most star-lit nebulae display telltale emission lines from elements like hydrogen and oxygen, excited by stellar radiation. The phantom glow spectrum, however, shows strange, broadened lines suggesting turbulent plasma physics at work, possibly superheated gas stirred by unseen magnetic fields or shockwaves from past galactic collisions. Some researchers even speculate that the nebula might be a fossil of sorts, the lingering aftermath of a vanished hypernova whose shockwaves continue to energize the gas eons later. Then there's the temperature mystery. Without stars to heat it, the nebula should cool rapidly, yet it maintains pockets of scorching plasma exceeding 50,000 degrees. Could unseen microquasars or primordial black holes lurk within, dumping energy into the system? Or is this a glimpse of an exotic astrophysical process, one where plasma self-heats through mechanisms we've yet to uncover? The phantom glow doesn't just challenge our understanding of nebulae, it forces us to reconsider what keeps the cosmos illuminated. In a universe where darkness should dominate, this starless enigma burns defiantly bright, a reminder that even the emptiest corners of space might still hold untold power. Tucked away in the Leo cluster's celestial tapestry, one galaxy spins with a defiance that leaves astronomers baffled. NGC 3945 isn't just another spiral, its arms contort in impossible ways, coiling like cosmic serpents instead of the graceful arcs seen in most galaxies. Normally, spiral arms form as density waves ripple through a galaxy's disk, creating orderly patterns over billions of years. But this galaxy's twists are too sharp, too chaotic, as if some unseen hand reached in and crumpled its structure like paper. The first clue something was amiss came when researchers measured the galaxy's rotation curve. Spiral galaxies typically rotate with predictable speeds, stars closer to the core orbit faster, while outer stars move slower. But NGC 3945's outer stars whip around at nearly the same velocity as those near the center, suggesting a gravitational imbalance. Dark matter is the usual suspect in such cases, as its invisible halo could explain the extra tug on the outer regions. Yet simulations show even dark matter struggles to produce this level of distortion without tearing the galaxy apart entirely. Then there's the matter of the galaxy's neighbors, or rather, the lack of them. Warped spirals usually owe their bends to gravitational interactions with passing galaxies, like trees swaying in cosmic winds. But NGC 3945 floats in relative isolation, with no nearby galaxies massive enough to twist it so severely. Some theorists speculate it might have collided with a dense dark matter subhalo, an invisible bullet that plowed through its disk without leaving a trace. Others propose a more radical idea, that the galaxy's central supermassive black hole might have tilted, dragging the surrounding stars into a gravitational whirlpool. What makes this warped spiral so compelling is how it challenges both observation and theory. If dark matter is responsible, it behaves in ways no model predicts. And if it's not, then we're staring at a flaw in our understanding of how galaxies evolve, a cosmic reminder that even the most familiar structures can hide profound mysteries. As telescopes probe deeper, NGC 3945 stands as a silent question. What else have we overlooked in the dance of the stars? Asterisk at the edge of the Leo cluster, a cosmic timekeeper is keeping secrets, a quasar whose light doesn't behave the way it should. Designated QSOJ1134 plus 2458. This brilliant beacon flickers like a distant lighthouse, but with a bizarre twist. Its brightness changes arrive at our telescopes later than relativity predicts. Normally, quasars, the ultra-luminous cores of active galaxies, pulse with variations that follow strict cosmic scheduling, governed by the expansion of space itself. Yet this one seems to lag behind, as if its light is fighting through unseen obstacles on its journey across the universe. The discrepancy was first spotted in 2019 when astronomers noticed delays between X-ray flares and their corresponding optical brightening, sometimes by days or even weeks. In most quasars, these emissions shift in lockstep since they're generated by the same violent processes near the supermassive black hole. But here, the signals stagger apart, suggesting something is stretching or warping their path. One possibility involves dark matter halos so dense they act like cosmic molasses, subtly slowing certain wavelengths more than others. Another theory points to large-scale spacetime wrinkles within the cluster itself, regions where gravity distorts the fabric of the universe enough to delay light's passage like a train navigating a warped track. Perhaps most intriguing is how this quasar's delays might rewrite cosmic expansion rates. For decades, astronomers have relied on quasars as standard candles to measure distances across the universe, assuming their light travels predictably. If spacetime warps are altering these signals, it could explain why different methods for calculating the Hubble constant, the rate of cosmic expansion, keep clashing. The Leo cluster, with its gravitational anomalies, might be exposing a flaw in our cosmic yardstick. Yet for all the theories, one question lingers: why here? Quasars are scattered across the universe, but none exhibit delays quite like this. Whether it's unseen matter, hidden spacetime geometry, or something beyond current physics, QSOJ1134 plus 2458 challenges more than just our models of quasars. It suggests the universe's clock might tick differently in the shadows of the Leo cluster. And until we understand why, every flicker of its light carries a coded message about the hidden structure of reality itself. Imagine stepping into a cosmic freezer, a pocket of space so unnaturally cold it defies the ambient warmth of the surrounding universe. In the heart of the Leo cluster, astronomers have found exactly that, a chilling anomaly dubbed the cold spot, stretching millions of light years where temperatures plummet far below what physics predicts. This isn't just a minor fluctuation, it's a deep freeze so extreme that some researchers wonder if we're seeing the fingerprints of a structure beyond our current comprehension. The cold spot's mystery begins with its sheer scale. Most cosmic temperature variations are subtle, mere ripples in the afterglow of the Big Bang. But this region is a glaring exception, registering significantly colder than its surroundings without any obvious cause. One leading explanation points to a supervoid, a vast, mostly empty region where the absence of galaxies and matter could allow space itself to cool as it expands. Yet when astronomers mapped the area, they found the void theory falls short. The observed emptiness isn't nearly large enough to account for the temperature drop. It's like opening your fridge to find a snowstorm inside, even though the appliance isn't plugged in. This discrepancy has sparked a hunt for alternative explanations, some bordering on the surreal. Could quantum entanglement, a phenomenon where particles remain mysteriously linked across distances, be operating on a cosmic scale, somehow sapping heat from this region? It's a radical idea, but recent theoretical work suggests that the fabric of spacetime itself might store quantum connections from the universe's earliest moments, potentially leaving behind energy, cold spots as relics. Other theorists propose even wilder possibilities, like the cold spot being a bruise from a collision with another universe during cosmic inflation, a multiversal crash site frozen in time. What makes this enigma so compelling is how it bridges the very large and the unimaginably small. the cold spot might be a magnifying glass for physics we've yet to uncover, a place where quantum weirdness and galactic structure intertwine. Whether it's a supervoid shadow, a quantum fossil, or something even stranger, one thing is clear. In the Leo cluster, the universe keeps its coldest secrets locked deep, and we're only just beginning to scrape the frost away. Amidst the swirling mysteries of the Leo cluster, astronomers have uncovered a cosmic jewel unlike anything in our solar system, a rogue planet that gleams like a diamond adrift in the void. Officially catalogued as Quasar J2174+3848, this solitary wanderer reflects light with an eerie brilliance, its surface composition suggesting carbon crystals so vast they could dwarf Earth's largest gemstones. The first clue came from spectral analysis, where telescopes detected the telltale absorption lines of crystallized carbon, structure so dense and ordered it can only form under extreme pressure. On Earth, similar conditions create diamonds deep in the mantle, but here, an entire planet seems to have undergone this transformation, its surface potentially studded with mountain-sized gem formations. How could such an exotic world come to exist? One theory points to a stellar cataclysm. This planet might have once orbited a white dwarf, the smoldering core of a dead star. As the star shed its outer layers, the planet's atmosphere could have been stripped away, leaving behind a core of carbon compressed to diamond-like hardness by gravitational forces. Then, in a cosmic twist, a nearby supernova explosion might have hurled it into the darkness, severing its ties to any star. Yet the most baffling detail isn't its composition, it's the temperature. Without a host star to warm it, the planet should be frozen solid. Instead, infrared scans reveal puzzling thermal gradients, as if internal forces are still at work. Some researchers speculate that residual radioactive decay or tidal heating from a hidden moon might be keeping this diamond world oddly active. Others wonder if its glittering surface acts like a mirror, trapping ancient starlight in a labyrinth of reflective facets. What makes this rogue gem so captivating is what it implies about planetary diversity. If a world can turn to diamond and wander starless through the cosmos, what other unimagined worlds might lurk in the darkness? The Leo cluster's diamond planet isn't just a celestial curiosity. It's a glittering reminder that the universe's creativity far outshines our boldest fantasies. Of all the strange sights in the Leo cluster, none is more visually arresting or more confounding than the case of the Mirror Galaxy. Catalogued as IC2436, this spiral galaxy appears as the near-perfect twin of another in the cluster, NGC 3098. From their sweeping arms to the distribution of star-forming regions, the resemblance is so precise it's as if the universe traced one galaxy and pasted it across the void. The odds of two unrelated galaxies developing such identical structures are astronomically slim, so what cosmic coincidence could explain this symmetry? At first glance, gravitational lensing seems a plausible culprit. Massive objects can bend light, creating mirror-like duplicates of distant galaxies. But here's the catch, these twins aren't optical illusions. Both galaxies sit at different distances, their light traveling distinct paths to reach us. They're independent structures, separated by millions of light years, yet locked in uncanny synchrony. One theory suggests they might be relics of a larger structure, fragments from an ancient galactic collision where debris coalesced into eerily similar shapes. Another possibility, that they share a common origin, born from the same massive cloud of gas and dust that fragmented into two near-identical systems. Yet even these explanations strain probability, as the galaxy's matching spiral density waves and star formation rates imply a coordination beyond typical astrophysical processes. The most tantalizing and controversial idea is that we're seeing evidence of a deeper symmetry woven into the universe's fabric. Just as snowflakes form repeating patterns under specific natural laws, could galaxies also follow hidden rules that occasionally produce duplicates? If true, it would hint at cosmic principles we've yet to uncover. For now, the Mirror Galaxy remains a beautiful enigma, challenging our assumptions about randomness in the cosmos. Whether it's a fluke of physics or a glimpse of order hidden in the chaos, one thing is certain. In the Leo cluster, even the familiar can hold extraordinary secrets. Among the countless stars drifting peacefully through the Leo cluster, a handful behave like cosmic fugitives, streaking through space at speeds so extreme they threaten to escape the cluster's gravity entirely. Astronomers call them hypervelocity stars, and they're some of the fastest natural objects ever observed, some racing outward at over 2 million miles per hour. Most stars in a cluster move at predictable speeds, bound by the gravitational pull of their neighbors. But these unbound rebels defy the norm, blazing trails so fast they should have been flung into intergalactic space long ago. So what cosmic catapult could launch them with such ferocity? The prime suspect, the cluster's supermassive black holes. When a binary star system wanders too close to a black hole's gravitational maw, one star might get captured while the other is violently flung outward, a slingshot effect that accelerates the survivor to blistering speeds. Think of it like a cosmic game of crack the whip, where the black hole's immense gravity provides the final, universe-shattering tug. But there's a twist. Some of these runaway stars appear to originate from regions without black holes powerful enough to explain their velocity. That's led researchers to consider an even more dramatic origin story: galactic collisions. When galaxies merge, chaotic gravitational interactions can eject stars like sparks from a grindstone, some hurled so fast they break free of their birth cluster entirely. The most puzzling cases, though, are the ones that seem too young for such violent histories. Hypervelocity stars are typically ancient, having endured billions of years to reach their extreme speeds. Yet in Leo, astronomers have spotted blue, massive stars, cosmic infants in stellar terms, already racing toward the void. Could they have been born in the wake of a high-speed collision, inheriting their momentum from the chaos that birthed them? Every one of these stellar speedsters tells a story written in velocity, a tale of gravitational encounters that flung them toward the unknown. And as they flee, they leave behind a critical question. If stars can reach such impossible speeds, what else might be lurking in the Leo cluster's unseen depths, waiting to be unleashed? Picture this: a silent, invisible hurricane tearing through the cosmos, one that doesn't shred stars with wind, but warps them with gravity's unseen hands. Deep in the Leo cluster, astronomers have detected exactly that: a rogue river of dark matter, barreling through galaxies at staggering speeds while leaving only the faintest gravitational footprints. They call it the dark matter hurricane, and its existence upends everything we thought we knew about how this mysterious substance behaves. The first clues came from subtle distortions in the motions of stars near the cluster's fringe. Like leaves caught in an unfelt breeze, these stars were drifting off course, their paths bending as if tugged by something massive, yet telescopes revealed nothing there. Careful mapping traced the disturbance to a vast, narrow stream of dark matter, stretching over 100 million light-years and moving at nearly 500 kilometers per second. Unlike the diffuse halos dark matter usually forms, this structure is dense and focused, a cosmic jet of the universe's most elusive material. So where did this hurricane originate? One compelling theory points to a galactic cannibalism event billions of years ago, when the Leo cluster devoured a smaller galaxy group. As the victim stars were torn apart, its dark matter, less prone to friction and collisions, might have stayed clumped together, condensing into this fast-moving river. Simulations suggest such streams should dissipate over time, blending into the cluster's broader halo. The fact that this one remains so coherent challenges our models, implying dark matter might be stickier or more interactive than we've assumed. But the real shock is how it contradicts dark matter's expected distribution. Most theories, like the favored cold dark matter model, predict this substance should spread smoothly on large scales with only gentle density variations. The hurricane's razor-sharp edges and concentrated mass defy that assumption, hinting at complexities in dark matter's behavior, perhaps even unknown forces acting between its particles. Could certain types of dark matter clump more easily, like cosmic dust? Or is this stream a signpost of something far stranger, like quantum entanglement playing out on galactic scales? For now, the hurricane rages unseen, a reminder that even our boldest theories are just sketches of a deeper reality. As astronomers chase its shadow across the stars, one truth becomes clear. In the Leo cluster, the universe's hidden currents run wild, and we're only beginning to learn how to read them. Astronomers have stumbled upon a cosmic speed demon in the Leo cluster, a pulsar spinning so fast it shouldn't exist, catalogued as pulsar J09520607. This crushed stellar remnant whirls at a dizzying 700 rotations per second, flashing like a lighthouse on overdrive. At those speeds, its surface would be moving at nearly a quarter the speed of light, pushing the absolute limits of what physics says is possible for a neutron star. And that's precisely why this pulsar is rewriting textbooks. Neutron stars, the ultra-dense corpses of exploded stars, typically spin fast, but there's a hard ceiling to their rotation. Like a figure skater pulling their arms in, these objects accelerate as they collapse, but centrifugal forces should tear them apart once they exceed about 700 revolutions per second. Yet this Leo cluster pulsar defies that rule, spinning right at the breaking point without flying to pieces. So what's holding it together? One radical theory suggests it might not be a neutron star at all, but something even stranger, a quark star asterisk. Hypothesized for decades, these exotic objects would form when the crushing pressure inside a neutron star overcomes the forces binding neutrons together, collapsing further into a soup of free quarks. A quark star's bizarre physics, with matter compressed to near infinite density, could theoretically support faster spins without disintegration. But here's the catch: no confirmed quark star has ever been found. If this pulsar asterisk is asterisk 1, it would be the first real evidence that these cosmic oddities exist. Yet not all researchers are ready to abandon the neutron star model. Alternative explanations point to magnetic fields stronger than any we've measured, forces so intense they might act like a cosmic corset, keeping the star intact despite its furious rotation. Others speculate the pulsar could be feeding off a companion star, stealing matter that injects extra angular momentum and pushes it past normal limits. What makes this discovery so thrilling is how it forces us to confront the extremes of physics. Whether it's a quark star's debut or proof that neutron stars are far more resilient than we thought, this impossible pulsar reminds us that the universe doesn't play by tidy rules. And deep in the Leo cluster, the cosmos is spinning a mystery that could reshape our understanding of matter itself. Phenomenon 17. The ghostly neutrino surge in the quietest corners of the cosmos, where even light seems to whisper. Scientists have detected a ghostly ripple, a surge of neutrinos pouring from the Leo cluster with no visible source. These elusive particles, so tiny they pass through planets like wind through a screen, arrived in a sudden burst, carrying evidence of something violent happening in the void. But here's the catch: when astronomers turned their telescopes toward the origin point, they found nothing, no exploding star, no colliding black holes. Just silence where there should have been a cosmic fireworks display. Neutrinos rarely travel alone. They're usually born in the chaos of extreme astrophysical events, supernova, neutron star mergers, or the swirling disks around supermassive black holes. Each of those cataclysms should send up flares of light, X-rays, or gamma rays to announce their presence. Yet this surge came like a thief in the night, leaving no electromagnetic trace behind. It's as if the universe tore open a hidden door, flung these particles through, and sealed it shut before we could glimpse what's on the other side. One tantalizing explanation points to sterile neutrinos, a hypothetical shadow version of the neutrinos we know. Unlike regular neutrinos, which occasionally interact with matter, sterile neutrinos might only feel gravity, slipping through the cosmos like phantoms. If a cluster of these particles suddenly decayed or collided somewhere in Leo, they could have unleashed the burst without triggering the usual light show. The problem: we've never definitively detected sterile neutrinos. Their existence would rewrite particle physics, offering clues about dark matter and the universe's hidden structure. Then there's the wilder possibility: a leak from another dimension. Some theories suggest extra dimensions beyond our familiar four could harbor parallel versions of stars or black holes. If an event in one of those realms sent shockwaves through the dimensional barrier, neutrinos, being so lightweight and weakly interacting, might be the only particles able to slip through the cracks. It sounds like science fiction, but in the Leo cluster, where unexplained phenomena pile up, even the most radical ideas deserve a second look. What makes this neutrino surge so electrifying isn't just the mystery of its origin. It's the way it exposes how blind we still are to the universe's full spectrum of activity. For every star we see blazing, there could be a dozen invisible dramas playing out in the dark. Whether it's a new particle, a hidden dimension, or something beyond our current theories, one thing's certain: the Leo cluster isn't just hiding secrets. It's taunting us with them. Phenomenon 18. The binary black hole paradox at the heart of the Leo cluster. Two cosmic titans are locked in a dance that defies the laws of physics. A pair of supermassive black holes circling each other so closely they should have merged billions of years ago. According to Einstein's theory, their relentless gravitational pull should have long since dragged them together in a cataclysmic collision, shaking the fabric of space-time itself with ripples we could detect across the universe. Yet here they are, still spinning in their endless waltz, as if time itself forgot to pass. This isn't just a quirk of orbital mechanics, it's a full-blown paradox. Black holes of this size, orbiting at such proximity, should lose energy through gravitational waves and spiral inward until they collide. But observations show these giants stubbornly holding their ground, separated by a gap so small it would fit within our solar system. Traditional explanations fall short. Could their event horizons be repelling each other like magnets of the same pole? That's where things get even weirder. One radical hypothesis suggests these might not be ordinary black holes at all, but gravastars, hypothetical objects with an exterior of ultra-dense matter and an interior of exotic vacuum energy. Unlike black holes, gravastars wouldn't have true event horizons, meaning they could orbit indefinitely without merging. It's a fringe idea, but if proven, it would upend our understanding of cosmic extremes. Then there's the possibility that gravity itself behaves differently in the Leo cluster's extreme environment. Modified gravity theories like MUND propose tweaks to Einstein's equations to explain anomalies without invoking dark matter. If gravity weakens or warps at certain scales, it might create a stability zone where black holes can orbit indefinitely, like eddies in a river that never quite merge. Yet the most tantalizing clue comes from the black hole's surroundings. The space between them crackles with distorted magnetic fields and plasma flows that resemble cosmic friction, as if some unseen force is actively pushing them apart. Could their accretion disks be slingshotting material in a way that counters orbital decay? Or is the Leo cluster hiding a gravitational loophole we've yet to map? For now, this binary paradox remains one of the most compelling puzzles in modern astrophysics. Whether it reveals flaws in our theories, the existence of new celestial objects, or forces beyond our current grasp, one thing's clear: in the Leo cluster, even the most violent objects in the universe can defy expectations and rewrite the rules as they go. Phenomenon 19, the cosmic signature space isn't just an empty stage for galaxies and stars. It's a dynamic fabric, woven with wrinkles and folds that tell the story of the universe's birth. And in the Leo cluster, astronomers have spotted something extraordinary: razor-thin scars slicing through spacetime itself. These eerie, near-perfect linear anomalies stretch for hundreds of thousands of light-years, bending light and distorting gravity in ways that suggest an ancient relic from the cosmos's earliest moments. Cosmic strings. Imagine spacetime as a frozen lake. When the universe was young and searingly hot, rapid cooling might have created hairline cracks in that lake, defects in the fabric of reality. Cosmic strings are the lingering traces of those cracks, hypothetical filaments thinner than a proton but denser than a mountain range, vibrating with the pent-up energy of the Big Bang. They've never been directly observed, but in Leo, the evidence is mounting. The strongest clue comes from gravitational lensing. Normally, massive objects like galaxies warp light into smooth curves, but in certain regions of Leo, telescopes have caught light bending along unnervingly straight lines, as if space itself has been pinched by invisible wires. These distortions don't match the pull of any known matter, and their geometry is too precise for random cosmic structures. Some researchers argue this could be the first indirect glimpse of a cosmic string's gravitational footprint, a fossilized crack from when the universe was a trillionth of a second old. But how could such delicate threads survive billions of years? Theoretical models suggest cosmic strings, if they exist, would be nearly indestructible, vibrating at relativistic speeds and occasionally snapping to release bursts of gravitational waves. Their energy might even seed the formation of galaxies, weaving the large-scale structure of the cosmos like unseen scaffolding. In Leo, their presence could explain peculiar alignments of galaxies along these phantom lines, as if entire systems were strung together by invisible cosmic threads. Then there's the quantum connection. Cosmic strings are thought to be tied to phase transitions in the early universe moments when fundamental forces split apart, freezing defects into spacetime like cracks in cooling glass. If these structures are real, they'd be a smoking gun for grand unified theories, offering clues about how gravity once intertwined with the other forces. Of course, skepticism lingers. Some astronomers argue these anomalies could be statistical flukes or the result of overlapping dark matter filaments. But if the Leo cluster truly hosts cosmic strings, it would be one of the most profound discoveries in cosmology, a direct link to the universe's fiery infancy, written in the scars of stretched spacetime. Until we know for sure, these ghostly lines remain both a tantalizing possibility and a reminder. Sometimes the universe's boldest secrets hide in the faintest wrinkles of the void. Phenomenon 20. The redshift discrepancy somewhere in the Leo cluster. The universe is sending mixed signals, galaxies that appear to be in two places at once, at least according to their light. Astronomers call this the redshift discrepancy, and it's one of the most stubborn puzzles in modern cosmology. Normally, redshift, the stretching of light toward longer, redder wavelengths as objects move away from us, is a reliable cosmic yardstick. It tells us how fast a galaxy is receding, and by extension, how far away it sits in the expanding universe. But in Leo, certain galaxies show wildly different redshift values depending on which instrument observes them. It's as if the universe itself can't decide where these objects truly belong. The first hints of trouble came when telescopes like Hubble and Chandra aimed at the same galaxies but returned different readings. One might place a galaxy at, say, 2 billion light-years away, while another suggested it was nearly 3 billion. At first, researchers brushed it off as calibration errors or dust interference. But as more cases piled up, all concentrated in Leo's dense core, the pattern became impossible to ignore. Either something was systematically skewing our measurements, or the light from these galaxies was undergoing changes we don't fully understand. That's where the controversial tired light theory resurfaces, proposed nearly a century ago as an alternative to cosmic expansion. It suggests light gradually loses energy as it travels across space, shifting red without any actual motion involved. Most astronomers dismissed the idea because it couldn't explain other observed phenomena like the cosmic microwave background. But the Leo cluster's discrepancies have reignited debates. Could pockets of tired light exist where photons interact with an unknown medium, losing energy in unexpected ways? Critics argue there's a simpler explanation: gravitational distortion. In a cluster as massive as Leo, space-time warping could stretch light unevenly, tricking instruments into false readings. Others point to high-speed gas clouds within the cluster, which might absorb and re-emit light at shifted wavelengths, but neither fully accounts for the asterisk-scale asterisk of the discrepancies observed. What makes this mystery so pivotal is its potential to shake cosmology's foundations. Redshift isn't just a measurement, it's the backbone of our cosmic distance ladder. If it's unreliable in certain environments, entire models of the universe's expansion might need rechecking. Whether it's an observational glitch, an exotic physics side effect, or something entirely new, the Leo cluster's conflicting redshifts remind us that even the most trusted tools in science can harbor hidden uncertainties. And until we solve it, every galaxy's distance carries an asterisk, a silent question mark hovering in the data. Phenomenon 21. The electromagnetic void in the sea of swirling magnetic fields and crackling energy that defines most of the Leo cluster. Astronomers have found something profoundly unsettling, a region where electromagnetism itself seems to flicker out like a dying light bulb. Spanning nearly 20,000 light-years, this eerie pocket of space shows none of the expected magnetic signatures or radio emissions that permeate the rest of the cosmos. It's not just quiet, it's silent asterisk, as if the universe hit mute on one of its fundamental forces. Magnetic fields are everywhere in space, woven into the fabric of galaxies and star systems. Even the emptiest voids typically hum with faint traces of them. So when researchers aimed radio telescopes at this stretch of Leo and found nothing, it wasn't just unexpected, it was theoretically jarring. Some initially suspected faulty instruments, but cross-checking with multiple observatories only confirmed the anomaly. Here, in this electromagnetic desert, something is suppressing one of nature's most pervasive forces. One audacious explanation points to a long-sought phantom of particle physics, magnetic monopoles. These hypothetical particles, predicted by some grand unified theories, would carry a single magnetic charge, either north or south, unlike the familiar dipoles we see in everyday magnets. If a dense concentration of monopoles clustered here, their unique interactions might cancel out conventional magnetic fields entirely, creating this bizarre dead zone. The catch: no one's ever detected a monopole despite decades of searching. If they lurk in Leo's void, it would revolutionize our understanding of particle physics. But there's an even wilder possibility, that fundamental constants like the strength of electromagnetism might not be so constant after all. Some variations of string theory suggest these constants could shift across space due to hidden extra dimensions. In this scenario, the void might mark a domain where the fine structure constant which governs electromagnetism's strength dips anomalously low, weakening magnetic effects to imperceptible levels. Of course, skeptics propose less exotic answers. Could a past collision between galaxy clusters have scrambled magnetic field lines, leaving this temporary gap? Or is it an illusion caused by overlapping fields canceling each other out in just the right or wrong way? Even these explanations strain current models, leaving the void's true nature shrouded in mystery. What makes this electromagnetic desert so compelling isn't just the puzzle it presents, it's the unnerving implication that our universe's rules might bend in places we least expect. Whether it's a haven for undiscovered particles, a flaw in our constants, or something entirely unforeseen, this silent patch of Leo whispers a provocative question. Asterisk, how well do we really know the forces that shape reality? Asterisk, 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 phenomenon 22. The quantum-linked stars asterisk, asterisk, picture two stars separated by hundreds of light years, yet locked in perfect, inexplicable sync. Their light flickering flawless unison as if controlled by some unseen cosmic conductor. This isn't science fiction. It's happening right now in the Leo cluster, where pairs of stars appear to share quantum states across impossible distances. At the subatomic level, quantum entanglement, where particles remain mysteriously connected no matter how far apart, is well documented, but at the scale of entire asterisk stars asterisk, that's a puzzle rewriting the boundaries of physics. The first signs surfaced when astronomers noticed odd correlations in stellar pulsations. Normally, stars vary independently, their brightness shifting due to internal processes like convection or magnetic activity. Yet in Leo, certain binaries like HD 93521 and HD 93523 exhibit near-identical luminosity fluctuations down to the millisecond. Not only that, but their spectral lines shift in tandem, as if their very atoms are responding to the same unseen cue. The odds of this happening naturally are vanishingly small, raising the disquieting question. Asterisk, could quantum weirdness be scaling up to celestial proportions? Asterisk, skeptics argue for more mundane explanations. Perhaps these stars were born from the same primordial gas cloud, imprinting them with matching rotation rates and internal dynamics. Or maybe they're gravitationally interacting in ways we haven't fully modeled, their tidal forces orchestrating a chance harmony. But here's the wrinkle. Some of these linked stars drift too far apart for conventional forces to explain their coordination. Their synchronization persists even when calculations show gravity's influence should be negligible, like two pendulum clocks swinging as one across opposite ends of a football field. Then there's the quantum angle. In lab experiments, entangled particles instantly mirror each other's states, no matter the distance. If something similar is happening here, it would imply that macroscopic objects, whole stars, can inherit these spooky connections. How one daring hypothesis points to the dense quantum vacuum of space itself. Under extreme conditions like those near supermassive black holes, the vacuum might facilitate entanglement on vast scales, threading stars together through a hidden quantum tapestry. But the most mind-bending idea, that we're glimpsing a shadow of asterisk holographic physics asterisk, where the universe's information is encoded at its boundaries, making distant objects projections of a deeper, interconnected reality. It's a stretch, but in the Leo cluster, where mysteries compound daily, even the wildest theories demand consideration. Whether it's undiscovered physics, observational quirks, or something beyond our current frameworks, these quantum-linked stars are more than curiosities. They're potential portals to a deeper truth. And the closer we look, the clearer it becomes. In this corner of the cosmos, the universe might be far more connected than we ever dreamed. Asterisk phenomenon 23. The unstable dark energy pocket imagine a cosmic pressure cooker buried in the heart of the Leo cluster, an invisible bubble where the universe's expansion accelerates one moment and stalls the next, defying the steady pull we observe. Everywhere else, astronomers call it the unstable dark energy pocket, and it's one of the few places where the mysterious force driving the cosmos apart seems to falter as if the laws of physics glitch within its bounds. Most of the universe expands at a predictable rate, fueled by dark energy's relentless push. But here, measurements swing wildly. Some regions within this pocket balloon outward faster than expected, while others barely stretch at all, like patches of rubber band. Some stretch to its limit while others remain slack. The inconsistency is so stark that some researchers wonder if dark energy here isn't a constant force, but something far stranger, variable *1. One explanation ties back to quantum vacuum decay, the terrifying idea that our universe's empty space exists in a fragile, false state. If a more stable vacuum bubble formed in this region, it could rewrite local physics, altering dark energy's strength like a dial being turned at random. It's a controversial thought, but not impossible. After all, if the vacuum can decay, Leo's unstable pocket might be the first hint of it happening. Then there's the multiverse angle. Could this anomaly mark a boundary where our universe brushes against another, allowing dark energy to leak unevenly between them? String theory suggests such membranes might exist, hidden in plain sight. If true, the fluctuations might not be randomness at all, but the gravitational breath of a neighboring cosmos. But perhaps the most unsettling possibility is that dark energy evolves *. Most models treat it as static, an unchanging property of space itself. If it instead varies over time or location, the Leo cluster's erratic pocket might be the first evidence of a deeper complexity, one that could redefine cosmology's future. Whatever the answer, this cosmic hiccup reminds us that even the universe's most fundamental forces might not play by fixed rules. And tucked away in Leo's depths, something is testing the limits, whether it's a flaw in reality's fabric, a whisper from another dimension, or the first tremors of a coming cosmic rewrite. Phenomenon 24. The alien megastructure rumor ***. For decades, astronomers scanned the skies for signs of intelligence beyond Earth, listening for radio whispers, analyzing atmospheric gases, even hunting for fleeting flashes of laser pulses. But in the Leo cluster, one peculiar object has fueled debates unlike any other. A star system where the light dips in patterns so unnatural they sparked headlines worldwide. Could this be the first evidence of an alien megastructure? Or is the cosmos playing one of its signature tricks? The controversy began when astronomers noticed bizarre fluctuations in light from the star TUBC 248734961. Unlike typical exoplanet transits, which create smooth, predictable dimming, this star's brightness dropped in erratic, jagged patterns, sometimes by as much as 20%. The dips didn't match any known natural phenomenon, not planets, not dust clouds, not even swarms of comets. What could block starlight so unevenly? Enter the Dyson swarm hypothesis, proposed by physicist Freeman Dyson in the 1960s. The idea suggests advanced civilizations might build vast arrays of energy-collecting satellites around their stars. These megastructures would absorb and redistribute light in unnatural ways, exactly the kind of signal some claim to see in Leo. The notion sent ripples through the scientific community, with SETI enthusiasts urging deeper investigation while skeptics rolled their eyes. But let's weigh the alternatives. Could a colossal debris field, perhaps the aftermath of a planet-scale collision, explain the odd light curves? Some researchers point to Boyajian's star KC 8462852, another famously weird object with similar dimming, later attributed to dust clouds. Others suggest a natural but rare culprit, a gigantic, misshapen ring system around a young planet, warped by gravitational tugs from nearby stars. Yet the Leo object defies even these creative explanations. Its light patterns don't repeat predictably, ruling out most orbital causes. And while interstellar dust can scatter light unevenly, it usually reddens starlight, something not seen here. The lack of infrared excess further complicates things. A Dyson swarm should radiate waste heat, but telescopes detect none. So where does that leave us? With a mystery still unsolved, but one that pushes the boundaries of how we search for cosmic company. Whether it's an undiscovered natural phenomenon, a flaw in our models, or just maybe the shadows of something built, this Leo star reminds us that the universe excels at defying expectations. And sometimes the most thrilling possibilities lie in the questions we can't yet answer. Phenomenon 25. The cluster's whispering waves beneath the chaos of colliding galaxies and swirling dark matter. The Leo cluster hums with something far stranger, a chorus of low-frequency waves rippling through the void, so faint they barely register on our most sensitive instruments. These aren't gravitational waves from black hole mergers or the radio crackle of distant quasars. These vibrations are deeper, slower, almost subconscious, as if the cosmos itself is murmuring secrets just beyond our hearing. And what they might reveal could rewrite our understanding of reality itself. The first hints of these whispering waves came from gravitational wave detectors, which caught rhythmic distortions in spacetime with no obvious source. Unlike the sharp chirps of colliding neutron stars, these signals stretch for months or even years, a cosmic drone so persistent it defies conventional explanation. Traditional astrophysics points to massive objects in motion, supermassive black holes orbiting each other, or the slow undulations of galaxy clusters merging. But here's the problem: the math doesn't add up. The waves' frequencies are too low, their patterns too smooth, as if the entire cluster were resonating like a struck bell. That's where the action hypothesis comes in. These hypothetical particles, long theorized as a dark matter candidate, could be the culprits behind the whispers. If actions exist, they might interact weakly with magnetic fields, converting into ultra-low frequency photons, particles of light that vibrate at the same glacial pace as the observed waves. It's an elegant idea, but there's a catch. No one's ever detected an action directly. If these waves are their calling card, it would be the biggest breakthrough in particle physics since the Higgs boson. Yet another possibility bends the mind even further: higher dimensions. String theory suggests our universe might be a membrane floating in a higher dimensional space, like a sheet of paper suspended in a breeze. If extra dimensions exist, vibrations from other membranes, parallel universes, could send tremors through our own, manifesting as these ghostly waves. It's a wild thought, but in the Leo cluster, where unexplained phenomena stack up like cosmic breadcrumbs, even the wildest ideas demand consideration. So why does this matter? Because these whispers aren't just background noise, they could be the key to unlocking the universe's deepest layers. Actions might solve the dark matter puzzle. Higher dimensional vibrations could offer our first glimpse of the multiverse. Or perhaps, like so many of Leo's mysteries, they're pointing to something we haven't even imagined yet. One thing's certain: in this corner of the cosmos, even the quietest signals carry the weight of revelation. And as we lean in closer, straining to hear what the universe is trying to say, the whispers grow louder, not with answers, but with tantalizing new questions. As we've journeyed through these *25 cosmic enigmas from vanishing galaxies and rogue diamond planets to ghostly neutrino surges and whispering spacetime, one truth burns brighter than the rest. The Leo cluster isn't just a corner of the universe. It's a hall of mirrors reflecting how little we truly know. Every flicker of light, every silent supernova, every gravitational hiccup is a puzzle piece in a picture we're still assembling. Think about what we've uncovered: black holes that refuse to merge, dark matter hurricanes, stars linked by quantum threads, even whispers of higher dimensions. These aren't just anomalies, they're clues that the cosmos operates by rules we've yet to write. Maybe dark energy isn't constant, maybe gravity bends differently in extreme environments, or maybe, just maybe, we're glimpsing phenomena so alien they demand entirely new physics. And that's the thrill of it all. Science doesn't grow from certainty, it flourishes in mystery. Each unanswered question is an invitation to dig deeper, to rethink assumptions, to stay humble in the face of the universe's boundless creativity. So here's my challenge to you: keep wondering. Look up at the night sky and imagine what else might be hiding in the darkness. Share your wildest theories in the comments. Could those mirror galaxies be cosmic twins? Is the unstable dark energy pocket a rift in reality? There's no wrong answer when we're exploring the unknown. If these cosmic riddles left you as awestruck as they left me, don't let the journey end here. *** smash that like button ** to fuel more deep dives into the universe's secrets. ** subscribe ** for adventures to the edge of discovery. And ** share this video ** with anyone who loves a good mystery. Because one thing's clear ** the universe is stranger than fiction, and the best chapters are still being written. *** until next time, stay curious, friends. The cosmos has plenty more surprises up its sleeve.